not there with me. Okay.
Sir, actually, I was late registered, sir.
Okay. You didn't got the institute email ID or not?
Yes, sir. I didn't get email ID, sir. Actually, I got a mail yesterday that I would receive, but I didn't receive, sir.
Okay. Because now the material which is there, I'll be sharing with the institute email ID only. Okay.
Okay, sir.
Try to get it and share it to me. Okay. Once after getting the institute email ID.
Yes, sir. Most probably I will get it today, sir.
Okay. Fine.
Okay, thank you, sir.
Yeah. Yeah, in the last class, actually, we have seen about the significance of the power quality, and in that significance of power quality, we have seen like why we need to concern with the power quality, and then and then the evaluation procedure to improve the power quality. It is like the evaluation procedure in the sense like we were trying to uh, identify where we need to install the a power quality improvement device. That is the actual thing. Okay. That we have seen in the last class also. Today we will try to go for the some of the power quality terms which are very much required also to know about why to know about the definitions. Okay. First, before going to the terminology or terms and definitions, we there is a need of consistency in the vocabulary. Okay, why we require to have the consistent vocabulary in the sense like whenever you are being manufacturing any kind of an equipment, uh, any kind of an equipment, uh, the individual customer should know about uh, if there is any voltage variations or any kind of the fluctuations or any kind of a system variations, is it capable to give out the performance required or not. Okay, for that we require to have a consistent vocabulary. Okay, why we require to have the consistent vocabulary in the sense like nowadays like there is a rapid growth of using of power electronic equipment, and then the distributed generations was increasing drastically. So the interest in power quality in the recent years and as accompanied by the development of special terminology to describe the phenomena. Okay, and then the terminology has not consistent across the different segments of the industry. Every I mean, you can see the industry have their own terminology to define the power quality. There are some the what do you say, some non-profit organization, especially when you look into the non-profit organizations, uh, IEEE. This is a IEEE, which is a Institute of Electrical and Electronics Engineers. This is a US a non-profit organization, and we have the IEC. The IEC is the International Electrotechnical Commission, which is of UK based. Okay, this is also a non-profitable organization, and SIGRE is there. SIGRE, actually, the term in that abbreviation here, the Congress International des Grandes. This is a French name. In the English, we be calling it as the International Conference on Electric System, but not the large high voltage. These are the different non-profit organizations. They work for IEEE standards, and they work for solutions for the uh, different solution for different kinds of a problem associated in the electrical system. Okay, it is not related to the power quality, it is almost all the areas. Okay, they try to work and they try to, especially the SIGRE and they work in the solution based, whereas the IEEE and IEC, I mean, in fact, the IEC works very hard to to prepare a standards for everything, for electrical equipment, even the uh, electrical equipment, and what kind of the supply need to be given to the customer also. Okay, even the manufacturers who are I mean who are making out the equipment, they look into the IEC standards, whether the equipment is meeting, or it is standardized to these particular standards or not. Okay, and we in this power quality, we have these kind of the standards which are been available. Basically, these standards are based upon the electromagnetic interference or the different frequency components. Why this electromagnetic interference has come into the picture is, what we expect is the signal to be a fundamental in general in sinusoidal voltage, whatever we get as power supply. Apart from that, there are the different frequency components which are going to associate with respect to the voltage. Okay, because of that, we be calling it as electromagnetic interference, kind of a terminology which will be based upon that. We have been classified, or IEEE or IEC and SIGRE have classified the power quality issues or terms and definitions also. Okay, uh, these standards, why we required these standards are required very much when you are manufacturing industry, when you are manufacturing any kind of equipment. The customer may not know what kind of the standards they says about the end user, who have been using that equipment. We see that, is it this standard is satisfied by the particular equipment or not also. Okay, generally the customer who are been there, apart from the industrial loads or the domestic loads, we doesn't know what it is also. In the last some 1 month back, when we have been purchasing for the institution level, we are purchasing around 60 kVA. In that case, we have specified some of the IEC standards. Okay, basically the health wise, and then some safety wise also, IEC standards have been mentioned, and that equipment, the UPS, has to pass these particular IEC standards. Okay, I mean, when you say that satisfies the safety wise, and then the environmental wise also, it is good also. I mean, these kind of the standards are very much useful for the end user when he is buying an equipment also. Okay, he doesn't know the different kind of a power quality issues also. Okay, yeah, these are some of the IEC standards. Principal phenomena causing the electromagnetic disturbances. Okay, this, I mean, I was mentioning about, apart from the fundamental, if there is any kind of other kind of signals which are dealing to the which are causing to the electromagnetic disturbances. Based on that, they have classified the different. These are the power quality issues connected to low frequency phenomena. No, I mean, I'm just okay. Read out the harmonics and then the interharmonics signal systems. It is a power line carrier, basically the power level frequency, and then the voltage fluctuations, which are flickers. I mean, voltage dips and interruptions. Voltage imbalance is equal to unbalance also. Power frequency variations, and then induced low frequency voltage, DC in AC networks. Okay, these are the issues, or these are the power quality definitions or terms also. And radiated low frequency phenomena, which are dealing with the magnetic fields as well as the electric fields. Conducted high frequency phenomena, induced continuous wave voltages or current, unidirectional transients or oscillatory transients. Okay, these are the high frequency components. Okay. Okay, we will try to see some of the kind of the power quality definitions or terms. Why? What is the reason why these kind of the disturbances are going to occur in a system also? Okay, we'll see when we're discussing about the definitions or the terms of the different kind of disturbances. And then radiated high frequency phenomena, magnetic fields, electric fields, electromagnetic fields, and continuous waves, and then the transients. This is a discharge phenomena. Okay, it is also one of the disturbance which is going to come arise in the system also. Nuclear electromagnetic pulse. Okay, these are the some of the electromagnetic disturbances classified by the IEC. Okay. Yeah. There is one term which is which just now we are we have seen like the voltage dips. And this is in voltage dips. Okay. Yeah. In the ISC terminology, they call it as a term, whereas in the US power industries, they call it as a SAG. Okay, they call it as a SAG. Okay, and this SAG is much difference with the under voltage. Dip, you know, what do you mean by the dip is there is a reduction in the voltage. Okay, okay. Especially these kind of a dip, which is of a interruption in the voltage. It is for very short durations. Okay, what I mean this slide says about it, the dip as well as sag are the both are the same only. When you go for American US standards, they call it as a sag, whereas the IEC, which is this they categorize it as a dip. Both are the same only. Okay, nothing difference between the sag and the depth. We'll try to see the other, whatever the content which is there in this particular slide in the next coming slides when we are discussing about the definitions. Okay. If I discuss here, it will be again the repetition. I'll just skip over here. The only thing is over here is the sag and the depth are both are the same. Okay, in the UK they call it as a dip, and the American they call it as the sag. Okay, these are C84.19. These are having some of the limits with respect to the what to say, the voltage, long duration voltage variations. I mean, ANSI they say about American National Standards Institute also. IEEE has taken over some of the standards from this particular American National Standards also. They have taken the copyrights and they have released IEEE standard of 519-1992. Okay, I have shared these particular standards to you, the Google Drive, and the same link which I uploaded in the Moodle also. This IEEE standard of 519-1992 is a combination of ANSI as well as the IEEE also. IEC also. Okay. Yeah. These are the standards which are based on the what to say, based on the IEEE, based on the IEEE standard also. Okay. These are categorized with respect to the spectral content, the harmonic spectral content, and then the duration, and then the magnitude of the voltage. Okay. Spectral content in the sense like between the two initial points, how much is the rise? How much is the rise is there? Like what kind of the frequency components are being associated? Before actually, there is one thing which, yeah, this has to come. power quality issues, when you say about a power quality issues, uh, we'll be having a steady state phenomena as well as non-steady state phenomena. Okay, a non-steady state phenomena which is dealing with the transient. Okay, the steady state phenomena which is dealing with the which is dealing with the steady state or for the longer duration also. Steady state in the sense throughout uh, the time, throughout the time is throughout the more number of the cycle also. Whereas the non-steady state is for a shorter duration, and between the two steady state points, if there is any variation in the voltage or the current, which is dealing to the a non-steady state phenomenon. The main attributes in the steady state phenomena are used is amplitude, frequency, spectrum, modulation, source impedance, notch depth, and notch area. Okay, these are very much deals with the uh, deals to the uh, I mean, voltage kind of a, if I take about a voltage, it all depends upon the variation with respect to the depth and then the area of the steady state point, and you can categorize based on the spectrum also. Spectrum in the sense like harmonic spectrum, and then the frequency also, and then the amplitude of individual frequency component or amplitude with respect to the fundamental voltage also. Okay, these are the attributes which are very much deal to categorize the steady state phenomena. And the non-steady state phenomena, other attributes are required. Apart from these attributes, we have one thing is the rate of rise, amplitude is there, and then the duration is there. Spectrum anyway it is there with the steady state, also there in the non-steady state, frequency and rate of occurrence, how frequently it is the variation is there. And then the energy potential, energy in the sense like between the two steady state point, how much is the energy is involved also. Okay, based on that also they will be categorizing the all steady state phenomena. Just a minute. Yeah. Yeah. According to that, here the IEEE has given some of the standards here. We have a transient here, 1.0. The transients has been categorized to impulse transient and then the oscillation transient. Okay, these transient which are of a non-steady state phenomena. You know about this one. Once you say about a transient, it is a non-steady state phenomena. Okay, and then in the transient also they have been categorized to impulse and oscillatory. And the impulse is categorized nanosecond and microsecond based on the rise time and then the typical duration also. In the oscillatory transient, they have categorized to the frequency components and then the time of the duration and then the magnitude. It is not so required to measure to remember all these things also. Okay, you just have an idea what kind of the impulse, what are the different kinds of the transients. I mean, different. How, yeah, I mean, you just know about what are the classifications of the impulse transients based upon the spectral content, whether which of the rise time has been considered over here. Okay. Whereas in the oscillatory, based on the frequency component, they have categorized low frequency, medium frequency, and high frequency. Okay. Overall, these transients are a non-steady state phenomena. And coming to the short duration voltage variations, this is voltage variations only. Don't think about anything about the current. Okay. short duration voltage variations, they have the instantaneous and then the momentary and then the temporary. Okay, these are in the instantaneous we have interruption, sag as well as swell. In the momentary also we have the interruption, sag and then swell. Whereas temporary also we have interruption or sag and swell, and the only thing is the duration over here. Duration in instantaneous it is of a half cycle to 30 cycles, momentary is 30 cycles to 3 seconds, whereas temporary is 3 seconds to 1 minute. Duration is less than 1 minute, less than 0.1 per unit, we'll be calling it as in interruption. Sag is 0.1 to 0.9, and then swell is 1.1 to 1.8 per unit. Okay. Overall, the short duration voltage variations are going to occur between a 0.5 to a 1 cycle. Okay, 0.5 to 1 cycle. We have another, with respect to the voltage variations, we have another is a long duration variations. So far, you might be knowing about these are the things: over voltage and under voltage, and then the interruptions. Okay, but not about this particular interruptions, sag or swell. You might not have heard about this particular terms also. Okay, these are the very commonly you have been studied or you have heard about this. The interruption, sustained interruption, also they can call, and under voltage and over voltage. If the voltage variations which are greater than 1 minute, we'll be calling it as a long duration voltage variation. And with respect to the magnitude over here, they are categorized. If the sustained interruption is 0, under voltage is 0.8 to 0.9. I'm not pretty sure about the magnitude over here. 0.8 to 0.9, there may be mistake is there. We'll try to see this particular 0.8, or it can go up to 0.1 also, or 0 also. No, greater than the 0.0, we can call it as a under voltage. We'll try to see this particular aspect of voltage magnitude of under voltage while discussing about the definitions. The over voltage is 1.1 to 1.2 per unit. Okay, this will be a longer duration voltage variations. And next we have the voltage unbalance. The load, this voltage unbalance is a steady state phenomena where I mean this particular long duration voltage variation also, which are very much deal to a steady state phenomena only. Okay, because these are there for a longer duration. Longer duration means it's a 1 day or 1 hour or even 2 hours or 3 hours also, these variations. But whereas these particular short duration voltage variations, this will be there for a few cycles, up to 1 minute. Even then we can consider it as a steady state phenomena. Okay, because the variation is of at the fundamental level, there won't be any frequency components. There won't be when you say about a non-steady state phenomena is the variation between the two steady state points is very narrow down. It's very narrow, very hardly it is of microseconds or a milliseconds. Okay. Okay, and then the magnitude wise, the variation is not very much peaky. The variation is very less also. Because of that, the short duration voltage variations also can be considered as a steady state phenomenon. Yeah, the voltage unbalance, the load is, it is kind of a load. It is 0.5 to 2%. How do we measure the voltage unbalance? We'll try to see when we're discussing about the definitions. Okay. Next, fifth one, we have a waveform distortion. Coming back to this voltage unbalance, the unbalance can be or will be there in the current also. It's not like the unbalance will be there in the voltage. The unbalance can be there in the current also. Okay, but as such, like there is no such a kind of a limits in specifying the current unbalance. Okay, why? Because the current unbalance is all depend upon the load distribution in the phases. Okay, the load distribution in the phases. The voltage unbalance. The voltage unbalance, it is a very severe problem to the individual customer. If it is a three-phase induction motor, will be having a circulating currents. Will be having the circulating currents, and a huge amount of the energy is going to waste. That is not advisable also. Why? Because one of the major problem is we have a pulsating torque is going to generate in a case of a three-phase induction motor when you allow the voltage unbalance. Okay, that is the reason they specify the voltage unbalance. Allowed is 0 to, I mean, 0.5 to 2%, and which is a steady state phenomena. And also when you're looking to the IEEE standard of 519, for the different voltage levels, that is the distribution voltage levels or the transmission voltage levels, they categorize, or they have, I mean, for the different voltage levels, there are the different voltage unbalance ranges have been specified. Okay, yeah. Next is the waveform distortion. This waveform distortion is also with respect to the voltage as well as the current also. Okay. The waveform distortion is not like with respect to the voltage only, it is respect to the current also. Okay. Here they have given that almost the waveform distortion is 5 categorized to 5: DC offset, harmonics, interharmonics, notching, and then the noise. And the harmonics are specified as 0 to 100 harmonic. Interharmonics is 0 to 6 kilohertz. Notching, they doesn't have specified the frequency. Noise is a broadband frequencies. Okay, these are all the waveform distortion or the steady state phenomena, and they have given the ranges with respect to the DC offset, how much is allowed, and 20%. 20% is I'm not sure about it, is all the harmonics contents or the individual harmonic content. But when we see the IEEE 519 standards, they have specified the harmonic content, what kind, they have specified the limits with respect to the individual harmonic current allowed in a system, allowed in the system. Okay, as such, like it is not so clear over here also. Okay, yeah. Next is the voltage fluctuations. Voltage fluctuations, or even the flicker also. This is of fluctuations or flickers or the intermittent change. It is not even the transient. It is the intermittent change in the variations. The load they have given around 0.1 to 7%. The 0.2-2-PST. This is basically the lamp flickerings. They have given that voltage fluctuations, how they can measure it is the lamp flickering. Okay, when there is a fluctuations, obviously we'll be having a flicker in the light. Based on that, they try to measure this particular fluctuation. Then the power frequency variations, which is the duration is of 10 seconds. Okay, less than the 10 seconds is allowed in any frequency variations also. Okay, these are categories and characterize of power systems of electromagnetic phenomena. based on the IEEE standard also. Yeah. In this particular unit, what we are going to see was we are going to see the definitions of transients. We are going to see the definitions of transients, and then long duration voltage variations, short duration voltage variations, and voltage imbalance, waveform distortion, voltage fluctuations, CBEMA, and ITA curves. And we see that we're going to see about what is the importance of these particular curves also. And the devices, it is unnecessary. I mean, the recent revision, we have added this particular content also, but may not be much relevant what we discuss with the definitions also. Anyway, we will try to discuss these particular devices for the over voltage protection also. Okay. Yeah. In the transients, you all know about it, the why there will be a transient in a system. Okay. As for I mean, if I look into this particular transient, it was looks like as I mentioned in the earlier classes, maybe the first class or the second class, I mentioned here, when you are connecting a huge amount of the energy source because of the inductance and the capacitance in a system, and the inductance and capacitance are not allowed to the change in the voltage or in the current. Because of that, it is going to influence either the voltage to shoot out the voltage or to shoot out the current also. Okay, because of that. Yeah, you have seen also. I mean, when you see about an excitation with a RL circuit or RC circuit, also we have seen the voltage or the current also how it is going to reach to the steady state when you are exciting a square waveform also. Okay. You can see this particular point, that part of the change in a variable that disappears during the transition from one steady state operating condition to another. The part of change in a variable or in a voltage or the current that disappears during the transition from one steady state to operating point to another steady state operating conditions. Okay. Another term, the synonym for the transient is called as surge also. Okay, I mean the lightning surge we say about lightning stroke also. Okay, that is going to cause about the over voltage or the insulation failure that is creating a short circuit over here. Because of the short circuit, we are going to see about the over voltages also. Okay, there is for the transient, there is another term which is there, this surge. Okay. Here one other point, end users frequently use the word indiscriminately to describe anything unusual that might be observed on the power supply, ranging from sags to swells to interruptions. Okay, end users, okay, the customers, they call it as sags also, because there are many potential ambiguities with this word in the power quality field. We'll generally avoid using it unless we have specifically defined what it refers also. Okay. Okay. I mean, if you categorize with respect to the time or with respect to the voltage magnitude, with respect to the variation in the magnitude or the harmonic spectrum, based on that, we can able to categorize or we can able to nullify the ambiguities, or there won't be any kind of ambiguities also. Broadly speaking, the transients can be categorized, we have seen in the earlier slide: impulsive transient and oscillatory transient. These terms of the transients, which are reflected to either in our current or the voltage also. We can, it's not like that we'll be having the voltage transients, we'll be having the both the current as well as the voltage transients also. Okay. Just a minute. Yeah. The transients are going to have the having current or voltage also. Yeah. Coming back to this impulsive transient, uh, this is a transient which is going to arise is based on the lightning phenomena, and the definition wise it says is a sudden non-power frequency change. Non-power frequency is fundamental. Non-power frequency change in the steady state condition of voltage, current, or both, that is unidirectional in polarity, primarily either positive or negative. If there is a voltage change, the voltage change, if you look into this particular waveform, yeah, the current here, it is changing only in the negative. Okay, okay, either in the negative or in the positive. It won't change the two sides, the positive as well as negative. The impulse transient is going to change in only either positive or the negative. Basically, the impulse transients are going to occur because of the lightning phenomena. Okay, in the definition wise, this is a very important point which you have to remember. Impulsive transient is a sudden non-power frequency change in the steady state condition of voltage, current, or both, even the both also, that is unidirectional in polarity, in brackets primarily either positive or negative. These impulse transients are normally categorized by their rise and decay time. How much fast it rising, how much is decaying, which can be revealed by the spectral content. I mean, when you see about the spectral content, which we can see about how fast it is rising, how fast it is decaying. Based on that, the impulsive transient will be categorized. You can see over here in the impulsive transient also, they have categorized a nanosecond, a millisecond, and a microsecond and milli, based on the rise time and then the duration over here. Okay, based on the duration. Impulsive transient also they categorize nanosecond, microsecond, and millisecond based on your rise time. 5 nanoseconds, 1 microsecond, 0.1 millisecond, and the duration, how much duration uh, the impulse transient will be there in the system. Okay, yeah, this is uh, the impulse transient. Next is yeah, I mean there is some of the few points. Because of high frequency involved, the shape of impulsive transient can be changed quickly by circuit components and may have significantly different characteristics when viewed from the different parts of the power systems. Okay, it is not see the inception where the lightning has been occurred. That means when you measure the voltage, if there is if there is impulsive voltage, and when you see in the upstream or the downstream, it looks like a different characteristics. Okay, sometimes in the downstream of the distribution system may not be going to feel that there is a impulse transient occurred in the upstream also. Okay, because we have a surge resistance, it attenuate over there it tries to suppress at that point where the fault, where the lightning stroke has occurred also. In that case, it won't carry it to the downstream. Okay, that is the point which says about it is we cannot. There is a different characteristics in the different parts of the power system. Okay, that's the second point. Also, you can see there are generally not conducted far away from the source of where they enter the power systems, not conducted far from the source where they enter the person, although they may, in some cases, be conducted for quite some distance along utility lines. Okay. Impulsive transient can excite the natural frequency of power system circuits and produce oscillatory transients. Okay, I mean sometimes, see, sometimes if it is a kind of a resonance kind of a phenomena where it can interact with other frequency component. Okay, the impulsive transient can excite the natural frequency of the power systems and produce the oscillatory transients also. It's not uh, the frequency uh, of the impulsive transients may sometimes, it is all sometimes only, it is not all the time, can excite the natural frequency of the power system and produce the oscillatory transients also. Okay. This is the same graph which I have shown in the earlier also. Yeah. Next is the oscillatory transients. This is an oscillatory transient is a sudden and non-power frequency change in the steady state condition of voltage, current, or both, that includes both positive and negative polarities. Impulsive is either positive or negative, but whereas the oscillatory, the variations between the two steady state points have the change in the voltage or the current, both the positive and negative polarities. Oscillatory transient is a sudden non-power frequency change, the steady state condition of voltage, current, or both, that includes both positive and negative polarities. Okay. Then oscillatory transient consists of a voltage or a current whose instantaneous value change polarity rapidly. Okay, it's not like about a fundamental frequency components only. That means that the variation may be of a 150 hertz or even 450 hertz. It won't be like that. It is going to have a high frequency component. When you say about high frequency components, then it says about a rapid change in the voltage magnitude or instantaneous voltage change magnitude or the current also. It is described by its spectral content, predominant frequency, duration, and magnitude. The oscillatory transients are going to occur the back-to-back capacitor energization and then the cable switching. Cable is nothing but a capacitor charging again, the same frequency range. Medium frequency transient can also be result of the system response to an impulsive transmission. Okay. We have in oscillatory transients, when you see about the definitions, we have a low frequency and then the medium frequency and then the high frequency. On the oscillatory transient, we have a low frequency, medium frequency based on the spectral content, 5 kilohertz, 5 to 500 kilohertz, and then the 0.5 to 5 megahertz, and duration, and then the magnitude also. One thing is here they have given one point over here in the oscillatory transient. Cable switching results in oscillatory voltage transient in the same frequency range. Medium frequency transients can also be the result of a system response to an impulsive transient. System response to impulsive transients. That's what we discussed in impulsive transients. Some of the transients, the impulsive transients, can excite the natural frequency of the power system and produce the oscillatory transients. The impulsive transients is the cause for the medium frequency transients. Okay. Yeah. These are the typical waveform of the back-to-back capacitor switching, which is result to the oscillatory transients. Okay. How does this current? I mean, it is a oscillatory transient with respect to the current when you say about the back-to-back energization. Okay. Oscillatory transients will with principal frequencies less than 300 Hz can also be found uh, in the distribution systems. They are generally associated with the ferroresonance and then the transformer energizations. Okay. Uh, the ferroresonance is also a different kind of I mean, it is a nonlinear kind of a behavior of the inductor. Because of that, we be having the ferroresonance. These ferroresonance also will be causing to the an oscillatory transient. Even the transformer energization also is going to have the uh, going to have an oscillatory transients. Okay, we have seen like uh, why there will be a transients, whereas the impulse transient as well as the oscillatory transients. Both the standards are with respect to the sudden kind of energy variations. Okay, both are with respect to the. If you take about a lightning, huge amount of the energy is going to come. If there is a capacitor energization, back-to-back capacitor, a huge amount of the current is going to draw from the source. That is going to result either into the voltage, that is going to influence either to the voltage or to the current also. Okay, or to the current. I mean, these kind of the because of that, we'll be having the oscillatory transient and as well as the transient in a system also. I mean, if you allow these kind of the transient in a system, is one thing is I mean, what kind of the problem which are going to face by the customers or by the individual customer. One thing is there is an insulation failure of any kind of an equipment. The insulation failure, it is not to all the equipments. Certain voltages, even the if you see about the variations, it hardly there from this particular time of 8.2 to the let us assume that it is there around 4 milliseconds. Some of the loads, it can able to withstand these current also. Okay, it won't have any problem. Even if you take about the impulse voltage, suppose if you assume this as something like a voltage waveform of 25 kilovolts, some of the loads it is bearable to these microseconds of 120 microseconds to uh, for this current, for this voltage also. Okay, if you take about the voltage magnitude variation or voltage transient also. Okay. Generally, the the transient is going to if the transients are occurring in the system, it is going to failure the insulation. If it is going to failure the insulation, it is going to have a short circuit in a system. Okay, the insulation failure in the sense like insulation means we have been isolating to the ground also. Because if you take about the overhead lines, why use the insulators means to insulators is to isolate the power line to the not into touching to the ground. Generally, we suppose the flashover or the lightning is going to occur on the insulator itself. It may even each individual insulator also have the I mean the disc or the insulator having the voltage. I mean having the threshold, having the voltage limit of the lightning voltage, whatever it is going to occur, or the surge or the transient, is for some sudden duration. If it exceeding the for the more the duration, then there is a insulation failure that is going to cause to the short circuit. When it is a short circuit, what is going to happen is we are going to have a experiencing of the voltage dip. because all the voltage is going to drop over here. In the downstream there won't be any voltage. Okay, that kind of the issues will be there. With respect to equipment also, even sometimes when you have a lightning, you have seen like the electrical appliances, some of the electrical appliances is going to damage or is going to burn out also. Okay, you might have heard in news, or you might have sensed it in some of the houses also. Since in the sense you might have observed also. Even one of my relatives' house also, when the lightning has occurred, their TV got damaged. Their TV got damaged also, because the huge amount of the energy which is going to come, and then it doesn't have that capability, then obviously it is going to seriously affect that particular equipment also. Okay, these are the issues which are going to occur because of the transients in a system. Yeah. Next is the voltage unbalance or voltage imbalance also. Okay, voltage imbalance or the imbalance. First, you will see why we'll be having the voltage imbalance. One thing is, uh, because of uneven connection of the loads, uneven connection of the single phase loads in a system. Okay, when you take about a three-phase system, I'm just making out a diagram. This is having a feeder impedance, which is of the same only, which is having the feeder impedance is of same value. Okay, ZS, ZS, and ZS. ZS is equal in all the phases. And we have here ZLA, and we have here ZLB, and we have over here ZLC. These are all ZLA and ZLB. ZLA, why this is coming over here this way? Yeah, ZLA is not equal to ZLB, is not equal to ZLC. Then what happened was, we'll be the current flowing through this, I mean we can say this is IA, the current flowing through this is IB, and IC is going to have the difference. It is difference there. Then obviously when you see this particular voltage of VSA, and this is VSB, and this is VSC, at this particular point, the terminal voltage VTA is not equal to VTB in terms of the magnitude. I'm just making out VTA is not equal to VTB in terms of the magnitude, maybe in the phasor also. Phasor in the sense like it will be, may not be 120 degrees apart. May not be 120 degrees apart. If you say about a balance, it have the equal magnitude. I may not be drawn exactly over here. Okay, this is VSA and VSB and VSC. These are the balanced voltages. When you allow the unbalanced currents, why we are allowing the unbalanced current? Because ZLA and ZLB and ZLC are not equal. Because of that, the currents are not same, and then the terminal voltage of VTA, which is equal to VSA minus of ISA or ZSA. Okay. Okay. I mean, I'm not sure about this particular equation. You just please look into that. What I mean to say that the terminal voltage of A phase, a B phase, and a C phase are not equal because of uneven load connections, or uneven in the sense like the different kind of impedance loads have been connected to the each individual phase. That is, phase A have certain impedance and phase B have certain impedance, phase A have ZLC. And this is one of the problem because of the single phase loads, uneven single phase load connection. There is another problem which is of a what to say, maybe the transformer turns because of the in the case of the distribution transformers, but it's a very rare case. But only thing is, because of improper behavior of behavior of tap settings. Okay, this is also one of the problem also. Even the feeder impedance also may not be the same. The feeder impedance I just mentioned over here, ZS, and same also. Because of the different, because the every line of individual line have its own kind of a characteristics. Because of that, the feeder impedance is also differ. Even then, the ZL and even ZL, the load impedance are same also. In that case also, will be having the terminal voltage unbalance. How do we measure this voltage imbalance, or the voltage is sometimes defined as the maximum deviation from the average of three-phase voltages. Is defined as the maximum deviation, okay, from the average of the three-phase voltage. Average is something around 220. One of the phases is 190, one of the phases is 200, one of the phases is 210. Then we get generally we get around whichever is the minimum, we'll get a maximum deviation also. Okay, may not be also, you please verify it. Whichever of a phase have the maximum deviation from the average of the three-phase voltage divided by the average of the three-phase voltage or current expressed in a percentage. This way, we'll be calling it as, we'll be evaluating the voltage imbalance or the voltage unbalance. That is even same to the current unbalance also. Okay, they have given the definition with respect to the voltage imbalance. The same is applicable in evaluating the current unbalance also. The imbalance is more rigorously, generally when you are going to study the voltage unbalance, is more rigorously defined in standards using symmetrical components. Okay, when you are going to study about the fault analysis, because the fault analysis in the sense like one of the phase may go into zero, the other phases are healthy. In that case, we are going to study by applying the symmetrical components. What exactly the symmetrical components is? It converts to a balanced system. Like a positive system is also a balanced system. We are the advantages of the symmetrical components is we are going to study the unbalanced system converting into a balanced system by applying the symmetrical components. We can evaluate the voltage imbalance or the unbalance from the symmetrical components also. That is, the ratio of either the negative sequence or the zero sequence component to the positive sequence component can be used to specify the percentage unbalance. The most recent standards specifies that the negative sequence method be used. Okay, the most recent standards specify that the negative sequence method. Okay, we'll stop over here. If you have any doubts, you can ask me now. It is basically what we are going to study this particular unit is most of the things are definitions only. Okay, all the content is there which I provided the material also. Okay. If you have any doubts, you can ask me now. Okay. Almost all 19 students are present.